Today we are going to introduce the concept of conditional probability. So, sometimes after conducting a random experiment or after observing certain random experiment, we have some partial information about the outcome of the experiment. Now, in the light of that partial information about the random experiment or about the outcome, if we want to find out the probability of certain event, then the probability gets modified. Let us take a very simple example. Suppose we say a die is rolled, suppose it is a fair die, and let us say B is the event that an even number occurs, and if I say E is the event that the number 2 occurs. Now, if I want to find out probability of E, it is equal to 1 by 6. However, if I know that an even number has occurred, then probability of E given that B has occurred is 1 by 3, because the B has elements 2, 4 and 6. That means my sample space has been restricted to consist of 3 elements 2, 4 and 6. Now, out of this, if we say 2 occurs, then it is one of the 3 possibilities, and therefore, the probability of that is equal to 1 by 3. So, you can see that the effect of the partial information makes us to make helps us in making better probability statements. So, let us define formally the conditional probability. So, if I say that omega B P be a probability space and let B be an event with positive probability, then for any event A, the conditional probability of A given that B has already occurred is defined by probability of A given B. So, this is the notation, probability of A given B, that is defined as probability of A intersection B divided by probability of B. So, now given any event B, if we are defining the probability of A, then first of all we should check whether it is a proper probability function satisfying the axioms of the probability. Let us check that. So, we state it as a result that P dot B is a valid probability function. Meaning thereby that it will satisfy the 3 axioms, that is probability of A given B, that is equal to probability of A intersection B divided by probability of B. Now, according to the assumptions of the probability, probability of A intersection B is always greater than or equal to 0, probability of B is strictly positive, therefore, this is always greater than or equal to 0 for all events B. So, the first axiom is satisfied. Let us look at the second axiom, probability of omega given B. This is equal to probability of omega intersection B divided by probability of B. Now note that B is a subset of omega, therefore the numerator will be probability of B divided by probability of B, and therefore it is equal to 1. The third axiom is the countable additivity axiom. So let us consider AI be a disjoint sequence of events. Let us consider probability of union AI given B. Now, by the definition of the conditional probability, this will be equal to probability of union AI intersection B divided by probability of B. Now, in the numerator I can apply the distributive property of the unions and intersection. So, this becomes probability of union of AI intersection B divided by probability of B. Now, here note that AIs were disjoint, basically we can consider them to be pairwise disjoint. So, if they are disjoint, then AI intersection B's will also be pairwise disjoint, and therefore, by the axioms of the probability, by the third axiom, I will have probability of union AI intersection B is equal to sigma I is equal to 1 to infinity probability of AI intersection B divided by probability of B, where each of the term then becomes probability of AI given B. So, you can note here that probability of the union is equal to sum of the probabilities, which is the countable additivity axiom. Therefore, the conditional probability function is a well defined probability function. Now, let us look at some direct consequences of this definition of the conditional probability. Let us consider, say, the statement probability of A given B is equal to probability of A intersection B divided by probability of B. Now, this statement we can write as probability of A intersection B is equal to probability of B into probability of A given B. So, an interpretation of this statement is that the probability of simultaneous occurrence of A and B is equal to the conditional probability of A given B multiplied by the probability of B alone happening. If we interchange the roles of A and B, then we can also write it as probability of A into probability of B given A, of course provided we consider that probability of A is positive. Now, this representation of giving the expression for the simultaneous occurrence probability in terms of a product, where in the product one term is a conditional probability and another term is a marginal probability, is known as multiplication rule. So, this is called multiplication rule. So, the general multiplication rule is let us consider events A1, A2, AN be events with now in order to define the conditional probabilities, the probabilities must be positive. So, we can take the smallest event which may occur in the definition and we can consider the probability of that to be positive, and then the probability of intersection AI I is equal to 1 to n can be expressed as probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2 and so on, probability of AN given intersection AI I is equal to 1 to n minus 1. Let me give this statement number 1. So, in order to prove this one, we can follow induction. So, by induction, if we want to see for n is equal to 1, the statement will reduce to simply probability of A1 is equal to probability of A1, which is trivially true. So, for n is equal to 1, the statement is true. For n is equal to 2, it is true, as we mentioned by the definition of the conditional probability, that probability of A1 intersection A2 will become equal to probability of A1 into probability of A2 given A1. Now, the statement for n is equal to 2 will be used for extending from k to k plus 1. So, let 1 be true for n is equal to k, and consider for n is equal to k plus 1. So, probability of intersection I is equal to 1 to k plus 1. Now, this one we can express as probability of A1 intersection A2 intersection A j, say j is equal to 3 to k plus 1. So, here if you see in the intersection, these are k minus 1 sets and this is 1 set. So, this is total k sets, and we have made the assumption that the statement is true for k. Therefore, we can write it as probability of A1 intersection A2 into probability of A3 given A1 intersection A2 into probability of A4 given A1 intersection A2 intersection A3, and so on up to probability AK plus 1 given intersection AJ, j is equal to 1 to k. And now, the first statement we can express as probability of A1 into probability of A2 given A1, and all the remaining terms will be there. Hence, the statement 1 is true for n is equal to k plus 1 also, and therefore, by the principle of mathematical induction, the general multiplication rule is true. The significance of this result lies in that many times we are not aware of the probability of the simultaneous occurrence. It may be somewhat difficult because what may happen that the events are conditional, that is, after occurrence of one, something may happen. For example, if a person is sick with a certain disease and he takes a treatment, what is the probability that he will be cured? Now, the probability of simultaneous occurrence of this event may not be so simple. However, if we know that the percentage of people who get cured by taking that particular treatment and how many persons eventually get recovered, then this probability can be calculated. That means, if I say A is the probability of getting cured, B is suppose A is the event of getting cured and B is the event of taking a particular treatment. Now, if we look at the percentage of people actually getting cured and the percentage of people who take the treatments and they are cured, or in the reverse way, if we look at the percentage of people who take the treatment and the out of the percentage of the people who take the treatment, how many get cured, then this probability can be evaluated. Let me write it as a example. Let A be the event person gets cured, B is person takes a treatment. So, now if I look at, suppose probability of A intersection B is to be determined, then we can write it as probability of B into probability of A given B. suppose we know that how many people take that particular treatment. Suppose 90% of the people take the treatment, and of the number of people who take the treatment, suppose 80% get recovered, then this probability turns out to be 0.72, which might have been difficult otherwise. And now this representation that a certain event can be considered as a consequence of certain other event or happening after a certain event, this leads to some interesting possibilities, and one of the major things is the so called theorem of total probability. So, let B1, B2 etc. be pairwise disjoint, that means mutually exclusive events with B is equal to say union Bi, I is equal to 1 to infinity. Here it could be a finite union also, it will not make any difference to the actual statement of the theorem. Then for any event A, probability of A intersection B can be decomposed as probability of A given Bj into probability of Bj, j is equal to 1 to infinity. Further, if probability of B is equal to 1 or say B is equal to omega, then probability of A is equal to sigma probability of A given Bj into probability of Bj. So, you can see here, if we treat the event A as a consequence of either of B1, B2 etc., then the eventual probability that A occurs can be represented in terms of that it has been caused by B1, it has been caused by B2 etc., and the corresponding probability of those causes themselves. We will look at some example here, and but firstly let me give the proof of this. So, consider A intersection B. Now, A intersection B can be written as A intersection, and the representation for B is union of B j, j is equal to 1 to infinity. By applying the distributive property of the unions and intersections, we can write it as union of A intersection Bj, j is equal to 1 to infinity. Now, we notice here that Bj's were pairwise disjoint sets, therefore, A intersection Bj's will also be pairwise disjoint, and therefore, the countable additivity axiom of the probability applies here, and you can write probability of A intersection B as summation of the probabilities of A intersection Bj. Now, by applying the multiplication rule on this simultaneous probability, this becomes probability of A given Bj into probability of Bj, which is actually the statement of the theorem of total probability. Now, we look at if probability of B is 1 or B is omega case also here. So, if probability of, if we take probability of B is equal to 1 or probability of B complement is equal to 0, then probability of A intersection B complement is 0, and therefore, probability of A can be written as probability of A intersection B plus probability of A intersection B complement as probability of A intersection B, and so the statement follows. Similarly, if we are saying that B is omega, then A intersection B is simply A, and the statement is true. So, let me give an example here. Suppose a calculator manufacturer purchases his ICs from suppliers, say B1, B2, B3 with 40% from B1, say 30% from B2 and 30% from B3. Suppose 1% of supply from B1 is defective, 5% from B2 and 10% from B3 is defective. What is the probability that a randomly selected IC from the manufacturer, say stock, is defective? Now, here if we consider the event, say A, that the IC is defective, then probability of A can be represented as sigma probability of A given Bj into probability of Bj, j is equal to 1, 2, 3. That means, since the IC could have come from either first manufacturer or from second manufacturer, second supplier or from the third supplier, and therefore, the consequence that it is defective is also, the probability is dependent upon who supplied that. So, this becomes probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. So, now probability that it is defective given that it came from the first one is only 0.01, and the probability that it was supplied by the first supplier is 0.4. The probability of being defective from the second supplier is 0.05, and the probability that supplier 2 supplied it is 0.3. Probability that it is defective provided it was supplied from the supplier 3 is 0.1, and the probability of getting the supply from the third supplier is 0.3. So, eventually this turns out to be 0.004 plus 0.015 plus 0.03, which is equal to so the eventual probability of the IC to be defective is approximately 0.05. Although individually if we see, from the first supplier only 1%, from second supplier 5%, and from the third supplier it is 10%. But since the procurement is mixed with the different percentages getting supplied from different suppliers. Therefore, the actual probability turns out to be 0.049. A further you can say consequence of this cause effect relationship is that sometimes we are knowing the final outcome. Now, what is the probability that this outcome was caused by something? Now, this representation, or you can say this way of looking at the probability, is called posterior probability, because here we can consider the events B1, B2, B3 that the supplies came from first supplier, second supplier or third supplier as prior events or something which is happening before. Now, being defective or not defective is an event which is occurring after that, because it is after procurement. Now, suppose it says that, suppose we take suppose the IC is supplied and somebody takes it and it is found to be defective. Then what is the probability that it came from first supplier, or it came from the second supplier, or it came from the third supplier? This way of looking at this probability is called posterior events, or the probabilities of the posterior events. So, the result for this is called Bayes theorem. Let me state the result first. Suppose B1, B2 etc. are pairwise disjoint events with union of Bj is equal to say omega. That means they are exhaustive also, and we are given a priori probabilities, probability of Bi as positive. Then for any event A, of course, since conditional probabilities are involved, we must say probability of A is positive. Then we define probability of Bi given A, that is equal to probability of A given Bi into probability of Bi divided by sigma probability of A given Bj into probability of Bj. J is equal to 1 to infinity. So, let us look at the representation of this. This means that we know the final outcome A. What is the probability that it was caused by the ith cause? So, this is the posterior probability, and this Bayes theorem actually helps us to calculate this. It is calculated in terms of the prior probabilities and the consequent probabilities, which are called like the cause effect relationship, that what is the probability that the event was caused by the ith cause. So, the eventual posterior probability can be represented in terms of this. This reverse relationship, it is due to Bayes, Reverend Thomas Bayes, and it was published in his treatise published in 1763 posthumously. The proof of this statement is let us look at the proof of this. So, we will just apply the definition of the conditional probability. Probability of Bi given A is equal to probability of Bi intersection A divided by probability of A, by the definition of the conditional probability. Now, what we can do is that in the numerator we can apply the multiplication rule in the reverse way. So, this becomes probability of A given Bi divided into probability of Bi. In the denominator you have probability of A. Applying the theorem of total probability, we can write it as sigma probability of A given Bj into probability of Bj. J is equal to 1 to infinity, which proves the statement of the Bayes theorem. One thing which one can notice here is that the proofs of the statements of the theorems are quite simple. This is happening because we have given an axiomatic structure to the probability, and therefore all the statements are simply consequences of certain relationships in the set theory. When the axiomatic definition was not known, all of these statements had complicated proofs, because if you use a relative frequency definition, then you have to look at the various relationships between the limits. If you use a classical definition, then you have to represent all the events in terms of favorable number of cases and the total number of cases, etc. So, all of these statements used to be quite complicated. The major contribution of the axiomatic foundation is that it made all the things extremely straightforward and also valid, because everybody can verify that the statements are true. Let us look at the previous example of the Ic defective problem. Suppose a randomly selected Ic is found to be defective. What is the probability that it was supplied by, say, supplier B1 or B2 or B3? Let us look at the first one. In the first one, we are interested in finding out the probability of B1 given A. So, this is by the definition of Bayes theorem, it will become probability of A given B1 into probability of B1 divided by probability of A. We already evaluated the probability of A as 0.049. So, it becomes simply probability of A given B1, that is 0.01 into 0.4, that is the probability of B1, divided by 0.049, which is equal to 4 by so it is 0.004 by 0.049, which we can write as 4 by 49. If we look at probability of, say, B2 given A, then in the same logic this will become equal to 15 by 49. If we calculate probability of, say, B3 given A, then by the same logic it will become 30 by 49. You can see here the difference in the posterior probabilities. Although only 30% of the product comes from manufacturer third, but if the finally selected Ic is found to be defective, then it is most likely to have come from the third supplier. The reason being that in the hypothesis of the problem, it has been assumed that more number of product from the third supplier are defective, which is actually 10%, whereas from the first supplier it is only 1%. So, although more supply comes from the first manufacturer, however, the probability that it came from him, provided it is defective, then the probability is much more small. So, this is an important you can say consequence of the Bayes theorem, that the posterior probabilities are quite different from the prior probabilities. Here you can see probability of B1 is 0.4, whereas probability of B1 given A is only 4 by 49, which is much smaller. Probability of B2 is 0.3, whereas probability of B2 given A is 15 by 49. Probability of B3 is 0.3, whereas probability of B3 given A becomes 30 by 49, which is much higher. So the probabilities get revised in the light of the knowledge about the outcome. So this is a good way of looking at the Bayes theorem as a cause and effect relationship. Now we have another concept called independence of events. Let us consider, suppose, tossing of two coins. Suppose they are fair coins. So my sample space here is HH, HT, TH and TT. Suppose I consider my event A as head on first coin and B is the event head on second coin. If I look at the probability of, say, A, head on the first coin is in HH and HT, so it is half. Suppose I consider probability of A given B, then it is equal to probability of A intersection B divided by probability of B. Now probability of B is simply equal to half, because we are saying head on the second coin. Head on the second coin is occurring in this and this, so it is half. And probability of A intersection B means head on the first coin and head on the second coin, which is happening only in one case, so the probability is 1 by 4. So this is turning out to be half, which is same as probability of A. Now this is different from the statements which I gave in the beginning of the conditional probability definition, that if I consider probability of E and probability of E given B, these two were different, it means that happening of B definitely affects the happening of E. Whereas in this one, probability of A and probability of A given B is the same. That means happening of B does not affect happening of A. This means the happening of A is independent of the happening of B. This is the concept of independence of the events. So if we proceed from the definition of the conditional probability, we must define event A to be independent of event B if we have probability of A given B is equal to probability of A. It translates into probability of A intersection B divided by probability of B is equal to probability of A, which is translating to probability of A intersection B is equal to probability of A into probability of B. Now if we also make assumption that probability of A is positive, then this will translate to probability of A intersection B divided by probability of A is equal to probability of B, provided we have assumed that probability of A is positive. So this will again imply that probability of B is equal to probability of B given A. That means B is independent of happening of A. So provided I consider that probabilities of A and probabilities of B are positive, the concept of independence of A with B or B with A is symmetric in nature. Therefore, to avoid unnecessary complications, we can consider this as the definition of probability as the independence of the events A and B. So we formally define events A and B are said to be statistically independent if probability of A intersection B is equal to probability of A into probability of B. So, you can see that this definition is symmetric in the independence of A with B or B with A, and moreover we do not have to write down the condition that probability of A is positive or probability of B is positive, because this definition does not involve the division here. Naturally, a question arises that if I have more than 2 events, then what is the meaning of independence? Let us consider, say, events A, B and C. Then events A, B and C are said to be statistically independent if probability of A intersection B is equal to probability of A into probability of B, probability of A intersection C is equal to probability of A into probability of C, probability of B intersection C is equal to probability of B into probability of C. Now, one may feel that these three conditions are enough for defining the independence of events A, B and C, but this is only pairwise independence of A and B, A, B and C. We need one more condition, namely probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. Now, this is required because it may happen that A is independent of B or A is independent of C, but then simultaneous occurrence of B and C may have something to do with A, or simultaneous occurrence of A and B may have something to do with C. Therefore, in order to define the statistical independence of 3 events, we have 4 conditions, namely we take 2 at a time and then all the 3 at a time. In general, then, if we have events say A1, A2, AN, then they are said to be statistically independent if probability of AI intersection AJ is equal to probability of AI into probability of AJ for all I not equal to j. You may write in one way only, because there is no need to write for I less than j and then for j less than I. So, you may put I less than j. Then taking 3 at a time, probability of AI intersection AJ intersection AK is equal to probability of AI into probability of AJ into probability of AK for all I less than j less than k. We may also consider 4 at a time and so on. Finally, probability of AI intersection I is equal to 1 to n is equal to product of the probabilities AI. The number of conditions, you can see this is NC2. So, how many total number of conditions are there? Total number of conditions will become the total number of conditions to determine the independence of n events is. So, let us look at how many conditions are there. Here we have n events and we are taking 2 at a time. So, total number of conditions is NC2. Here we have 3 from n, 3 at a time. So, the total number of conditions is NC3 and finally it is NCNR1. So, the total number of conditions is eventually equal to NC2 plus NC3 plus NCN, which we can write as 2 to the power n minus n minus 1. So, a total number of 2 to the power n minus 1 conditions are required to determine the statistical independence of n events. Of interest is also to look at infinite number of events and then talk about its independence. Then logically it means that if we consider any finite subset of or any finite collection of those infinite number of events, then that finite collection must satisfy the conditions for the independence. So, we define events A1, A2 and so on. That means the indexes are belonging to some set are said to be independent if for any finite collection, let me call it say AJ1, AJ2, AJN, the conditions for independence are here let me specify that the conditions which are all mentioned here must be satisfied in order to have the actual independence of the events. For example, if I take the case k is equal to 3, then for 3 events the statistical independence is defined in terms of pairwise independence conditions. There are 3 conditions and one in which all the 3 are taken. Now, one may say that if the pairwise independence conditions are satisfied, then the last one is automatically satisfied. Actually, it is not true. The satisfying of the first 3 does not imply the satisfaction of the fourth one or vice versa. This may be satisfied, but one of these may not be satisfied. Let me give examples of this. That is pairwise independence does not imply mutual independence of events. Consider say tossing of 2 fair dice. Let me consider the event A as say odd number on first die, B as the event odd number on the second die, and C is the event odd sum. Let us consider the probabilities of A, B and C. So, if we look at probability of A, odd number on the first die, it means you have 1, 3 and 5 on the first. The total number of possibilities here is 36, and odd number on the first means 1, 1, 1, 2, 1, 3 up to 1, 6, 3, 1, 3, 2, 3, 6, 5, 1, 5, 2, 5, 6. So, total number of 18 possibilities are there. So, probability of A becomes half. Likewise, probability of B is half, and likewise probability of C, that is the odd sum, is also half. If we consider the probability of A intersection B, then we are saying odd number on the first and odd number on the second. What are the possibilities? 1 1, 1 3, 1 5, 3 1, 3 3, 3 5, 5 1, 5 3, 5 5. There are 9 possibilities out of 36 possibilities. So, this becomes 1 by 4. If we look at probability of A intersection C, then we are saying that the first number is odd and the second and the sum is odd. It is possible 1 2, 1 4, 1 6, 3 2, 3 4, 3 6, 5 2, 5 4 and 5 6. So, this becomes 9 by 36, again 1 by 4. Similarly, probability of B intersection C is 1 by 4. Naturally, you can see that the conditions for the pairwise independence are satisfied here. So, A, B, C are pairwise independent. However, if we look at probability of A intersection B intersection C, then if we have odd number on the first die, odd number on the second die, naturally the sum will be even, and therefore there is no case where A intersection B intersection C is satisfied. Therefore, this probability is 0. Naturally, this is not equal to probability of A into probability of B into probability of C. So, A, B and C are not independent, although they are pairwise independent. Let me consider one example in which the condition for the simultaneous, that is the third condition may be true, but one of the earlier conditions may not be true. Consider, say, let us consider the set, let there be 4 identical marbles and we mark them and we mark them with symbols. That means on the first one we write A1, A2, A3 and A1, A2, A3. That is, on the first marble we mark A1, A2, A3, on the second one we put A1, and the third one we put A2, and the fourth one we put A3. We draw one of the marble identically, select at random one of the marbles, let EI denote the event that symbol AI appears on the marble. Let us look at probability of EI. It will be half for all i's. If I look at probability of, say, E1 intersection E2, probability of E1 intersection E3, probability of E2 intersection E3, each of this is going to be 1 by 4 because only one possibility is there. And therefore, if I look at probability of E1 intersection E2 intersection E3, then that is also 1 by 4 and it is not equal to probability of E1 into probability of E2 into probability of E3. So, this is another example where the events are pairwise independent, but they are not independent. Let me take one more example. consider say omega is equal to 1, 2, 3, 4. Let Pi be the probability assigned with the set consisting of I is equal to 1, 2, 3, 4. Let us define say P1 is equal to root 2 by 2 minus 1 by 4, P2 is equal to say 1 by 4, P3 is equal to 3 by 4 minus root 2 by 2, P4 is equal to 1 by 4. Let E1 be equal to 1, 3, E2 be equal to 2, 3 and E3 is equal to 3, 4. Then if I look at probability of E1 intersection E2 intersection E3, then it is simply the probability of 3, that is P3, that is 3 by 4 minus root 2 by 2, which I can write as half into 1 minus root 2 by 2, 1 minus root 2 by 2, which can be written as P1 plus P3 into P2 plus P3 into P3 plus P4. So this is equal to probability of E1 into probability of E2 into probability of E3. So the last condition for the independence of E1, E2, E3 is satisfied. But if I look at probability of E1 intersection E2, then that is also equal to 3, and therefore it is not equal to probability of E1 into probability of E2. Therefore the conditions for the independence are not satisfied here. So in effect it means that if we want to check the independence of events, then we must check the probability of simultaneous occurrences by taking all the combinations, by taking 2 at a time, 3 at a time and so on. Thank you.